Good morning. So thank you all for coming. I actually was unaware of the previous talk, which seems in many respects very similar to our work. At least I'm going to use some of the previous talk to skip some of my slides. So this is joint work with Anna Karlin, Elias, Koutsoupias, and Christos Papadimitriou. And you see everybody's putting photos up. So these are our photos. Okay. I also want to draw your attention to the great similarity between this presentation and Avi Wilkerson's presentation yesterday, given the colors and the fonts. So, okay. So this is an actual graph of Bitcoin mining difficulty over time. And clearly, the driving reason has to do with the value of the coin, which fluctuates, and the mining difficulty fluctuates, and the efforts fluctuate. And the question is, why do people drop out? Well, they drop out because the coin is worth less, and also because the costs are too high for the given level of effort. So there's a notion of an epoch. An epoch is a geological timescale term, and you can see all the different divisions here: epochs, periods, eras, and this is evolutionary development. But it's also defined in the Satoshi protocol. This is the Satoshi protocol. And an epoch is a period in which 2016 blocks are generated. Now, in the protocol, there's this notion of the Bitcoin difficulty adjustment, which we just heard about. And the epoch is supposed to last 2 weeks. It's about a block every 10 minutes. This is why you have delays when Bitcoin transactions take place. It takes some time. Several blocks have to be generated. And every epoch, the difficulty is adjusted so that if it took too short a time, then the difficulty increases. If it took too long a time, the difficulty decreases. So the reason this was put into the protocol, presumably, we don't know, but presumably is to deal with changing technology over time. And in fact, when you look at over a long period of time, you see that the next difficulty was determined based on the previous epoch, but it's going to take, in reality, less than 2 weeks, slightly less than 2 weeks, because in the meantime, technology has advanced. Even in these 2-week intervals, technology has changed. So we're not going to talk about 2 weeks. We're going to talk about one time unit, and of course, the effort is also impacted by the market value of the coin. Now, we can normalize. We can say, let's normalize regarding the market value of the coin. Let's just normalize everything by that. And so we're not going to talk about changing values of the coin at all. And as mentioned, there's a lot of proof of work, cryptocurrencies, Bitcoin being the most dominant one of them. But even things like Ethereum, which supposedly is going towards proof of stake, is actually based on proof of work. Now, there's strategic deviations to the Satoshi protocol. And the 51% attack is described in the basic protocol. And the famous paper by Alan Sure, "The Majority is Not Enough," describes other strategic variations. So the key idea behind their deviation, their attack, is to produce new blocks, but don't publish them immediately. Hold on and wait. So everybody else is working on this block, and in the meantime, some evil-minded person is sitting by the side and developing other blocks. And at some point, he'll make use of these blocks. So I'm going to talk about a new class of strategic deviations, which is manipulating the difficulty adjustment protocol. So it's very much like the talk we just had. And we'll study optimal deviations and equilibria in a variety of such settings. So we are actually looking at equilibria, and we're looking at such deviations. And some of our optimal deviations are based on conjecture, because the proof is by Mathematica. And difficulty adjustment attacks based on difficulty adjustment are not really new, in the sense that they appear in coin hopping deviations, which, it's a recent work, independent of our work, we were unaware of it. But this requires that multiple coins be available for mining. So basically, rather than just be laid back, you go off and produce something in another coin. So, and this actually has advantages, and they don't consider equilibria either. So the main critical issue is that if you exert efforts, the job becomes harder in the future. And if you goof off and do less work, then the job becomes easier in the future. So we exhibit equilibria that alternate between going full throttle and goofing off. Okay, in restricted settings, we give exact unique equilibria. In general, we show the constant effort is not in equilibria. In some scenarios, no pure equilibria exists at all. Pure equilibria means setting an effort that you extend. And we give a general closed form for best response based on some mathematical assumptions. So let me just recap. The inherent tension here is if you goof up, your investment is lying unused. Others may be hard at work and you will lose out. Counterwise, if you're hard at work, you're making things more difficult for yourself in the future. So this is the inherent tension. It has to be balanced. And if we talk about equilibria, then everybody's playing this game. And the bottom line, the take-home point, is that it's a bizarrely complex mess at equilibria. This is my room. And the outcomes are somewhat non-intuitive. So the question is, what does the Satoshi protocol actually say about the effort, etc.? And it's not clear, right? But does it imply constant effort across epochs? So obviously not, because technology change was built into the protocol. Technology was going to advance over time. But as I said, one could normalize for technology change. There's some rate of technology change one could normalize and say, is the normalized effort essentially fixed or not? And we don't know. I mean, this is a sacred text, but we don't know what's really written there. For some reason, this is not working. So the key take-home poem is the key take-home point is that this is not a best response, a constant effort, even if we adjust for changing technologies. So this is the model. There's some maximum number of hashes per time unit for a miner. There's the actual number of hashes per time unit. There's the total number of hashes per time unit. Again, this is not known, but you know how long epochs take, so you can adjust difficulty depending on time. There's the probability that a single hash will solve a crypto puzzle, which is determined in this way. It's 1 over the total hashes per time unit in the previous epoch. And the thing we're looking at is energy cost. So there's a cost for doing a hash. And alpha I is the energy cost of 1 hash for miner I. And so the energy cost is the energy cost per hash times the length of the epoch times the number of hashes per time unit, which is this thing. So it's the energy cost, the length of the epoch, and the number of hashes, product of these things. And the utility of the miner is the following. It's the probability that the agent gets the prize, which is his hash rate compared with the total hash rate, minus the energy cost. And this is what comes out. This is the result, just not doing the math. And what we really care about, exactly as in the previous talk, We care about the utility per time unit, because time is money. Right? We're looking at, for the next 5 years, how much are we going to profit per day? And this is the average. It's the total. What we have in the denominator here is simply the total length of time. So let me talk about a toy problem. And it's two identical miners. The max hash power is 1/2, only 2 epochs, and equal energy costs. So xi is the hash rate, well, x1 is the hash rate of agent 1, x2 is the hash rate of agent 2. The puzzle complexity of at epoch 1 is going to be fixed externally. Basically, it says if you put full power in, then you're going to solve it in 1 unit. Now, the length of epoch 1, the length in time of epoch 1 is the time of the previous epoch, in this case 1, over the total hash in epoch 1. So it's 1 over x1 plus x2. And the length of epoch 2 is, in fact, x1 plus x2. These are variables. They're unknowns. We don't know what they are. And we argue that, first thing, we say that, well, at epoch 2, both miners will go full throttle. And if you look at this thing and ask, how does my utility or my average utility depend on my effort at epoch 2, it grows with my effort at epoch 2. So I go full throttle, which means in this case, we're assuming that the maximum hash power is 1/2. So both will use maximum power 1/2, which is why here we're dividing by 1. Okay? So at the last epoch, we know what's going to happen. There's only one epoch that we're not unsure about. What should the miners do? So you can see that one can come up with a closed form for the expressions here for the utility, and this is the bottom line. So if the costs are too high, there's no hash equilibrium. There is no equilibrium. For a certain range of hashes of energy costs, these in this case they're the same, both energy costs. For a certain range between 1/2 and 3/2, there's a unique hash equilibrium in which the miners hold back. They don't put in the full power, but they spend less energy. They're goofing off to some extent. And for small enough costs, where the energy costs are small enough, then they will go full throttle in all the epochs. And this is what the graphs look like. This is the level of effort and equilibrium as a function of the energy costs. And you see that at first it's full throttle up to a certain point, then it drops. And it drops dramatically, gets close to 0. And this is the utility per time unit. And again, you see that it goes down quite a bit as the costs go up. And this is a picture just describing, again, the same thing. So this is an imaginary epoch. This doesn't exist, but we're assuming that they're going full throttle in this imaginary epoch. And what they do in this case, I've actually fixed the cost here. The energy cost is 3/4. And you'll note that they drop down. The total hash power being used in epoch 1, this unknown epoch, is 0.68, not 1. I mean, if they were doing full power, it would be 1. They drop down to this thing. And then we said at the last epoch, they go up again. And these are so obviously this threshold, this epoch is longer, exactly as we saw in the previous picture, in the previous talk. This epoch is longer. It's 1.45, not 1. This is just an example, by the way. I just fixed some parameters to show what's going on. And this epoch, of course, is going to be shorter. Okay, so I don't have much time. Let me just say that we know of a we consider the following, it's also a toy problem. Assume miners are restricted to using fixed power across all epochs. What does the equilibrium look like? And then again, we see that they will, in fact, that we can construct exactly what the equilibrium looks like. Some miners will drop out, those with higher energy costs. Some miners will play the game. And we know exactly what level of hash they'll be using. There's a closed form equation for what level of hash they'll be using. And we know what the utility is. And if you believe that for some reason the Satoshi protocol implies that you must use constant effort per across all epochs, then you know there's all sorts of takeaways you can take from this thing. For example, you note that the minor, if we're taking about a case where all agents are equal here, the utility per epoch is proportional to 1 over n squared. And of course, if they collaborated, it could go up to 1 over n. And another thing is if a new minor takes up a sizable fraction of the hash power, others will have a negligible, will actually use a negligible fraction of the hash power. And if you insert a second minor who's slightly below the most powerful minor, everybody else will drop out. So all these come out of the equations. Now, as I said, constant effort is not an equilibrium. There's many cases where we show that it's not. In fact, under very simple assumptions, very reasonable assumptions, a constant effort will never be an equilibrium. And it holds even for very small minors. So even if you have very small minors, they're going to deviate. Now, there's a precise form for what the best response looks like, subject to Mathematica. But Modulo Mathematica, this is the precise form. And the bottom line, again, is that it's a bizarre, complex mess at equilibria. I have no answers about reality. This reality is not part of this talk. I mean, and the outcomes seem non-intuitive. And there's lots and lots of open questions and conjectures and so on. And this, by the way, Anna didn't like her photo at the beginning. So this is Anna's photo, which I took yesterday with the family. Okay. Thank you. Yes. Yeah. In fact, the analysis is for the asymmetric case. The minors are asymmetric. When I later plugged in thing, I took them to be symmetric, but the analysis is for the asymmetric case as well. Yeah, the analysis I had for the toy. Oh, so I guess. Okay, that doesn't make sense what I just said. There is an analysis for the asymmetric case for two players. It's actually the more general analysis that I gave here. So the analysis I gave, I'm going too far back. Yeah, forget about this thing. This is the toy problem. Okay, yeah, we do have. I'm sorry, we do have an analysis for asymmetric case for two players. Yeah, yeah, of course, sure. It's not mine. Oh, sorry. Yeah, let's take it offline. I have to. Yes, thank you. Please. Okay, good. So this is the coin hopping attack, which basically wasn't talking about equilibria. They were talking about just a deviation, a profitable deviation. I don't know how that would behave, but clearly it becomes more profitable if rather than goofing off, you can spend your effort at the same time, mining Ethereum rather than mining Bitcoin. So inherent in their analysis, they talk about the coin hopping attack. They say, well, you goof off, and they use the term goof off, or you goof off on one coin, you use the extra energy on another coin, and vice versa. And obviously, you're gaining more. So this is a clear deviation that's profitable. And, yeah, okay. So I don't know what the equilibrium look like.